Sylvie Corteel from Centre National de la Recherche Scientifique at University Paris Diderot, with a paper with a presentation on partitions with constrained successive ranks and lattice paths.
So I want to thank the organizer for giving me this opportunity to talk, and also accept to switch the time of my talk. But unfortunately, I got finally the last talk of the conference, which might not be the easiest one. But anyway, I'm finishing this conference after a great series of talks today. So Doron gave a recap of yesterday's talk, but it's quite hard to get after such great talks this afternoon that were so pedagogical and so cool, and especially all the women's talk of Pamela, Greta, and Bridget. So, and I want also to thank Marnie for switching talks with me. So today I'm going to talk about this project about partition with constrained ranks and lattice paths. And I chose to talk about that because it's really an enumerative combinatorics subject, but also because it's something that shows on one hand that maybe COVID was not only bad, okay? So as we see today, I think we all prefer conferences that are in person. I wish I was not alone in my office at 6:20 p.m. rather than being with my kids. But also, thanks to this time, I restarted some collaborations on Zoom. And one of my highlights of the weeks for the last 2 years was to see Sergi and Carla every Wednesday and have a nice chat with them, both personal and mathematical. And so that's one of the good points of what's been going on during COVID, okay? So this is joint work with Sergi Elizalde for Dartmouth and Carla Savage from NCSU. Okay, so I'm gonna define in this talk the title of my talk. So I'm gonna define partition. I'm going to define what are ranks of partitions, what does it mean to be constrained, and also I'm going to do a bijection between this partition and certain lattice paths. And so you're going to see the interconnection, and hopefully by the end of the talk, you're going to understand what I am looking at, okay? Okay, so I'm just making a little remark before I start with definition, is that this is a subject that's been going on for a long time. Okay, this is very classical enumerative combinatorics. So I listed a few papers on things that are related to what I'm going to talk about. There are many more, but I want just to highlight the two bottom ones, if you can see them. I'm not sure you can really see them though. Okay, so I don't know if I can switch. Okay, so you can't see, I don't know if you can see the bottom of my slides, but anyway, there are two papers I wanted to cite. Is a paper of Carla in collaboration with Bruce Sagan called Mahonian pairs, and also a paper of, it's funny because on my screen, I see full screen. Thanks, Sheila, but I don't know. Let me try something else.
Can you zoom in or zoom out?
Zoom out, you have another suggestion? Just fourth in the second line, under settings, maybe that one.
Let me just
try full screen. Try full screen.
Maybe I'll try something else. Okay.
Now it's fine. And it's full.
Okay. Oops. So now things are moving faster than I want. Okay. So this is the end of the day talk, I guess. Okay. So anyway, it's because Sergi wrote that talk about measuring symmetry in lattice path and partitions that from FPSAC 2020 that was presented in 2021 that we started this collaboration. Okay. So let me go into definitions, even though most of you know the objects I'm talking about. So partitions, and I'm going to say a partition in this set P of Mn, okay, is a sequence, okay, lambda 1 up to lambda k. So I suppose my integers in my sequence to be positive. They are in non-increasing. The sequence is non-increasing. And I suppose that the number of parts, k, is less or equal to m, and the first part is less or equal to n. Okay? And then we say that a partition is a partition of capital N. If I sum all the lambda i's and I get capital N, and also something that's going to be important in this talk is the notion of Durfee square, so which is a statistic on my partition. And I say that the Durfee square of lambda, d of lambda is equal to d. If the df part of lambda is greater or equal to d, but the d plus first part is less or equal to d. Okay? So we're going to see that there's a better way to think about that. Okay, when we want to look at the Durfee square is when we use the Ferraz diagram of a partition. So Bridget just defined this idea. So let me take an example. So lambda would be the partition 6654441. So I say that lambda is in P of 69 because it has also maybe P of 96 because it has less or equal to 9 parts and the first part is less or equal to 6. Okay, so we see a first typo here. So I draw the Ferraz diagram of this partition. So in my first row, I put 6 cells and then 6 cells, etc., etc. And so why is that easier to define the Durfee square this way? So first, I guess the weight of the partition is just the sum of the parts, which is equal to 30. And the Durfee square of the partition is the largest square that I can fit in my Ferraz diagram. Okay, so these are very, very classical notions. Okay, so I'm going to look at partitions that are fixed in a box. Okay, and I want to enumerate them according to their weight, the sum of their parts, and their Durfee square. Okay, so that's my first idea. But now I want to define the successive ranks because I want to add some conditions on my partitions. Okay, so first I need to define what's the conjugate of a partition. So I said that a partition is a sequence that I read when I read the rows of the diagram. Okay, so that's how I would get 6654441. But the conjugate is the partition that I get when I read the columns of the partition. So the conjugate of lambda here, that I denote by lambda prime, is 7,666,32. Okay. And then the ranks of the partitions, so the successive ranks. So the number of successive ranks is exactly the size of the Durfee square. So here that would be 4. And I define the R successive rank to be lambda I minus lambda I prime. Okay, so the size of the ith row minus the size of the ith column. Okay, so if we just do this example, we've seen that the Durfee square, the largest square I can fit in the diagram is equal to 4. And the ranks are -1, 0, -1, and -2. Okay, so for example, the fourth rank is equal to -2 because the fourth part of lambda is 4 and the fourth part of lambda prime is 6 and -2 is equal to 4 minus 6. Okay. So one first thing you can ask is why would you care about such statistics? Okay, and they've been around for quite a while. And one of the motivations to do that is the following theorem, which says that the number of partitions of n whose successive ranks belong to 0 or 1, so each successive rank is equal to 0 or 1, is equal to the number of partitions of n whose parts are congruent to 1 or 4 mod 5. Okay, so this is one of the combinatorial interpretation of the famous Rogers-Ramanujan identity. Okay, so if I fix my successive ranks to be in the interval 0, 1, okay, then this is in bijections with partitions whose parts are congruent to 1 or 4 modulo 5. And so the general questions we are trying to study is if I fix a set of integers, so a countable set of integers S, okay, how many partitions of a given integer capital N in P of Nm have all their successive ranks in that set? Okay, so what I've just said before, okay, is that if set S is equal to 0, 1, and then my n and m go to infinity, okay, this is equal to the number of partitions into parts congruent to 1 or 4 modulo 5. So that's going to be my notations. Okay, I'd like to compute the generating function of these partitions. So they are in an m by n box, okay, and their ranks are all in a given set. So I cannot answer this general question. That's the question I'd like to answer, but we'll see we can have some partial answers. Okay, and what I'm going to use in this talk, my main tools, is I'm going to translate this problem of counting partitions in a box according to their Durfee square and their weight and their ranks in a given set to a problem of enumerating certain lattice paths according to their number of descents and their major index. Okay, so let me state what I wrote here, even though there's many, many words, is that there exists a bijection between those partitions in R and M of S, and with a fixed Durfee square of size D, okay, and certain lattice paths where I can go up or down, okay. I start at 0, 0, I end at m plus n and m minus n, where m and n are the same as here, and the Durfee square becomes the number of valleys of the path, the major index the size of the partition becomes the major index of the path. And if the ranks are all in the set S, then the valley heights are going to belong to another set, namely minus S minus 1. Okay. So let me explain to you why this is true. It's not a very hard result. It's just a simple bijection. Okay. And so I will use this notation that I want to count this path now with a certain m plus n steps, okay, and ending at height m minus n, and I want the valley heights to belong to a given set. Okay, so let's see an example of this bijection. So I claim that I can take a partitions whose successive ranks are in a given set, and then I take a path whose valley heights are going to be in a given set. Okay, and this is nothing else than what's called Foata second transformations for some words with letters 1 and 2. Okay, so here is my example. I start with the partition I used before in the examples with m equals 9 and n equals to 6. And I claim that if I apply Foata second transformation, I'm going to get this lattice path. And you can see, as I highlighted here, the Durfee square here will correspond to the number of valleys of the path. And then you can also check that the weight of the partition that was equal to 30 is going to correspond to the major index of the path, which is exactly the sum of the positions of the valleys. Okay, so here I have a valley at position 3, one at 6, one at 9, and one at 12. And hopefully, if I sum 3 plus 6 plus 9 plus 12, I find 30 again. So let me explain to you how you do this bijection.
Let me interrupt. I'm confused. It is a product transformation that links the inversion number and the major index, or the one about permutations?
Yes, yes.
Oh,
Because the weight of the partition is the inversion number if you read the border word. So you send inversions to merge.
oh, thank you.
So how can I build this bijection? Okay, so what we're going to do is we're going to follow the main diagonal of the partition here. Okay, and we're going to look what's on the right and what's below this main diagonal. Okay, so I wrote here what's on the right. I'm going to count just the number of cells to the right of my path here. I get 6, 5, 3, and 1. And I'm going to do the same below. Okay, and I get 6, 4, 3, and 2. Okay, and I claim that these two partitions are going to tell me exactly the positions of the valley of my path. So what I'm going to do is I'm just going to add the ith purple number to the ith blue number. That's going to take me the abscissa of the valley. Okay, and if I take their difference, then I'm going to get the height of the valley. Okay, so here I claim that it's going to tell me that I have a valley at abscissa 12 and height 0, a valley at abscissa 9 and height -1, etc., etc. Okay, and so you see straight away why the weight of the partition becomes the marge of the path. Okay, because the abscissas of the valleys correspond to all the hooks of the partition. Okay. Now let me tell you why also we can find the ranks. Okay, I said that the height of the valley correspond to the purple number minus the blue number, but this is really related to the rank because the rank was the ith row minus the ith column. So you can see straight away that if a valley is at height y, then the rank is going to be equal to minus y minus 1, plus 1, or no, minus y plus 1, minus 1, sorry. So here we have a valley at height -1, and so that gives us a rank at height 0. Okay, so I just decompose my partition into hooks, and I have the hook that's the horizontal part, the hook that's the bottom part. Okay, and I can construct my path easily just knowing the hooks of the partition. So now this translates my problem, okay, of enumerating partitions according to some ranks to enumerating certain paths according to their number of valleys, their major index, and also the possible heights of the valley. Okay, so let's do some simple examples. Okay, so the first simple example I wanted to say is that if I fix S to be the set -n+1 up to -1, then I'm going to say that the number of partitions of n, alors here I didn't write this, but in Rn of S, okay, is going to be exactly the nth Catalan number. Okay, because when I do that, if I take a partition where the ranks are all negative, okay, the path I'm going to get is exactly going to be a Dick path. Okay. So what I get from this bijection is just the set of Dick path. Okay, and I get back a QT Catalan number that was known before, where you enumerate Dick path according to their number of valleys and major index. Okay, and this was studied by Furlinger and Hofbauer. So this Q Catalan, okay, that was counting by descent and major, correspond also to partitions whose ranks are all negative and fixed in an n by n box. Okay. But now I can also look at partitions where all the ranks are positive. They're also going to be counted by Catalan numbers. So I get a weird corollary, okay, that says that the number of paths from 0, 0 to 2n0 that have up and down steps but now the valley heights all must be less or equal to -2 is also the Catalan number. Okay. So here is an example, okay, where n is equal to 3. I get 5 paths, okay, that go from 0, 0 to 2n, 0. The valley heights are less or equal to -2, and I get the Catalan number. So I could be like Doron saying, if you give me the bijection, I'll give you $1,000, but I'm not going to do that because the bijection is actually really easy. Okay. So let me give you the bijection for free. The bijection says that if you have a valley in XY in the blue path, then you will have a valley in X and -1, -2 in the red path. And this is an inflanon leaf. And if you know the positions of the valley and the start and end point, you can recover the path uniquely. Okay. So this is not a very hard problem.
Is it yet in the Stanley list of Catalan numbers? Or it's a new one?
I don't know.
I wonder how many difficulty points you will give to that.
But anyway, that was one example of something fun you can find. But then you can find some pretty harder things. Okay, now if we take L to be an integer, and I take S to be the set from 1 minus L to n minus 1, then we can find again that this generating function, where L has some extra conditions here, is going to be again a TQ Catalan number, but kind of switched. Okay, now n is replaced by n plus L, and then the t is changed by tq to the minus L. Okay, and then if we choose some other values of L, then L is less or equal to 1, but greater than m minus n. Then you can compute again this generating function, and you can according to the Durfee square and the size of the partition. And then you're going to get some nice sum, okay, where here we have a difference of products of Q binomial coefficients. Okay, so here I define the Q binomial coefficients. It's just a Q analog of the binomial coefficient. Okay. And then here we had the case finally when L was less or equal to 1. But if L is greater or equal to 0, okay, you can again compute this generating function. So we fix the box, S is this like that. So the ranks are going to be greater or equal to 1 minus L. And you can compute the generating functions according to the Durfee square and to the weight of the partition. Okay. And if I set t is equal to 1, okay, I can just do the summation here on I, and that tells me that the partition in a given box Q to the weight of the partition is going to be the difference of 2 Q binomial coefficients, except this one is switched by L plus 1. So in particular, if m and n go to infinity, we find back that the number of partitions whose ranks are greater or equal to 1 minus L are in bijections with the partitions that don't have any part equal to L plus 1.
Do you have a comment or explanation to this special case when t equals 1?
Yes.
Oh, that's nice.
So actually, we have several of them. Thank you, Doron, for. So actually, depending on the value of L, you have several ways of proving that. Okay, one way is to use the ranks and to look at the partition that's to the right and under the Durfee square as a pair of paths with certain conditions. And so what you have behind that is the Lindstrom-Gesell-Vienno lemma. But you can also, I guess, use the inclusion-exclusion as presented by Doron today, is that to see that this part on the right, so we have a minus, and we enumerate exactly what this part is. So these are the partitions who have at least a rank that's not in S. Okay, and bijectively, by a bijective construction, we can compute their generating function. And also, I want to point out a third way of attacking this problem was also a very classical construction due to Green and Kleitman, who showed an injection on how to go from a subset of size k of a set of size n, where k is less than 1/2, to a subset of size k plus 1. Okay, so you can use this idea due to Green and Kleitman to also study these paths. So let me tell you how you can see this construction of Green and Kleitman on lattice paths. So I take one of my paths here that have certain values, okay? And the idea of Green of Kleitman is to look at a down step, okay? That's the lowest possible, but if I have several lowest down step, I'm gonna choose the leftmost one, okay? And what I do is very simple. I take this down step and I just move it up, okay? And so what this is gonna do is gonna decrease the marge exactly by 1, okay? It's gonna move up all the valleys. And also, most of the time, okay, the number of valleys are gonna be conserved, okay? The only time where I'm gonna lose a valley, if I start by a down step, and this down step is the step that I want to change, okay? So in very specific conditions, the number of descents is gonna decrease by 1, but most of the time it's conserved, and I can also control when the descents are changed, okay? So by this idea, by just looking at a path, the lowest down step and the leftmost, if I have several of them and I change this down step to an up step, we can prove the result I wrote down. Okay. But then this is not my equations in general, okay? Here we can look at certain sets, basically where we force the ranks to be greater or equal to a value, okay? And our general question is still really not answered. So the question is, in general, could we compute these generating functions of partition with ranks in a certain set? Okay, so we know already that there's some beautiful combinatorics around there. So when m and n goes to infinity and the ranks are one interval, okay, we know that this is related to the Andrews-Gordon identities, the same way that 0, 1 was related to the Rogers-Ramanujan identities. Okay, and then we have also in the paper some examples where the set has 2 values, okay, that are just not always consecutive. But then there's a recent paper of Seo and Ye that looks at this notion of parity change. So here they look at the set of positive number and negative numbers, but they look at runs in the rank sequence, okay, where the first ranks all belong to a set, then the next sequence, the ranks do not belong to the set, and then the third sequence, the ranks belong to the set, and you look at the number of times it changes where the sequence are in the set, not in the set, in the set, not in the set. And actually, you can again use lattice path to compute this kind of sequences where you fix the number of parity changes in your rank sequence. So that's going to be paper number 2, but it's probably going to take a while. So I thank you for your attention. And also I thank the organizer for such a great conference.
Okay, thank you, Sylvie, for your great and wonderful talk. We have some space for questions.
Okay, since nobody else is asking a question, let me ask a question. In addition to your numerous statistics, can you also put in the area statistics and possibly the famous bounce statistics and see what's going on?
Oh, under the area under the path and the bounce statistic? Oh, maybe. Do you think there's any hope to do that?
Yeah, so you already have quite a few statistics. It's really beautiful connection between lots of classical objects. I also want to make a comment. The Darby square size has a new name now called the H index, and it's very useful nowadays. Thank you.
I'm sure you wrote a paper about that, no?
The Darby square is the same as the very fashionable and sometimes controversial H citation index of a researcher. So the Darby, do you know about that? There's the size of the
I think I know thanks to you, so.
Okay, thank you. Sure. And as I've Googled you, unfortunately, you have lots of papers, but right now in Google Scholar, you don't have an H index yet. You have to do it manually. So your Darby square number is pretty big, but it's not yet official. So maybe you should make it. Thank you.
Did you look about characterization when the ranks are, for example, constant or two values content?
So if the ranks are all constant, this is really just some variation of self-conjugate partitions. So self-conjugate partitions are the partitions where all the ranks are equal to 0. And so this is fairly easy to do.
Any other question? If not, again, thank you, Sylvie.